All right, so today we're going to be looking at the efficiency of heat engines and then the efficiency of kind of ideal engines, which would be like kind of what's their maximum efficiency. Uh, Everything else just kind of not being considered. And then what's the maximum work something can do? We're going to talk about that a little bit too. So we have four equations we're kind of looking at here. They're kind of alterations of each other in one way or another. But typically, these are going to be the four things we're going to be looking at here. The first one here, the amount of work that an engine can do is equal to the heat transferred to the hot reservoir of an engine minus the heat transferred to the cold reservoir. Um, Really what this is telling us, so all heat engines, what they do is when heat is transferred from a hot place to a cold place, work can be done. We can make that transfer of energy do work. This is how something as basic as a Stirling engine works. It's also how all internal combustion engines work as well. If we wanted to know the efficiency of that heat engine, what I could do is I could take the work done by that engine and divide it by the heat transfer to the hot reservoir. That ratio of work to the hot heat, if you will, or the yeah, um, that tells me how efficient it is. Okay, it's going to be a decimal. If I take it times 100, it becomes a percent. Or if I kind of substitute in, QH over QC over QH, I can do some algebra and I can have like QH over QH minus heat transfer to the cold reservoir over that. I know these will cancel out, just give me one. That's where this comes from. It's just basic algebra. Um, Sometimes though, that's a little bit easier because we're really wanting to know the differences between the cold and hot reservoirs, like because that's going to tell us how efficient it is. Those are pretty easy to measure. Ideally, we're not even going to be talking about heat transfer. We're going to be talking about temperature. So if ideally the maximum efficiency of a heat engine is 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir. It looks very, very similar. Heat, though, is energy, so it's measured in joules. Temperature, in this case, typically we're going to measure it in Kelvin. They just give us better ratios. In fact, it has to be in Kelvin. Thank you. Um, and then if I can do some more rearranging of things, I could calculate the maximum work done by a heat engine is 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir times the heat transferred to the hot reservoir. Pretty much just these four equations can just be used in different ways to either measure work or the efficiency, or we can do some algebra to figure out the things not given to us. So let's start looking at that problem there at the bottom. A heat engine with an efficiency of 24% performs 1,250 joules of work. Find A, the heat absorbed from the hot reservoir, and B, the heat given off to the cold reservoir. All right, so in this case, a couple things I need to do is first off, I need to figure out which equation or equations I'm going to use. To do that, I'm going to look at what's given and what they're asking for. So in this case, they give me the efficiency and they give me the how much work is done. So, and we're not talking about maximum efficiency. So I pretty much know I'm not using these bottom two equations, and they don't give me temperature. So I'm going to use one, if not both of these two. All right, so it's giving me work. It gives me efficiency. They first want to know the heat absorbed from the hot reservoir. All right, so in this case, if I have efficiency and I have work, I can algebraically find QH, okay? So efficiency is equal to work over the heat transferred from the hot reservoir. In this case, the work they said was, the efficiency. Let's just get QH by itself. Multiply QH by both sides. I get QH is equal to work over efficiency. so now to do this, my work we said was 1,250 joules of work. The efficiency they said was 24%. Convert that to a decimal, 0.24. All right, let me get out my calculator quick. So 1250 divided by 0.24. So 5,208, that's probably close enough. 5,208 joules of heat. Like that's how much is being absorbed from the hot reservoir. So now I have QH. So that's the answer to part A for this question. Part B asks, how much heat is given off to the cold reservoir? I can pretty much use either equation for this part now that I know QH. So I'll just use this top one here. If we know that the work done was 1,250 joules, this time we know, actually let's do this algebraically. Work equals QH minus QC. I need to get QC by itself, so I need to add QC to both sides, subtract W from both sides. QC will equal QH minus work. So in this case, actually that's a C. Good enough. We just calculated the heat transferred from the hot reservoir, so that was 5,208 joules. Have to subtract the work, which we said was 1,250 joules. All right, so this time don't have to do any multiplication or division. So 5,208 minus 1,250, 3,958 joules. So I know from this, my hot reservoir is transferring 5,208 joules of heat energy into my engine. But only, that should be a C, only 3,958 joules is actually getting transferred to the cold reservoir. So I've lost, roughly 1,250 joules, essentially just out to the surroundings. That's heat energy that's not being made to work. And that really falls in with the second law of thermodynamics. As pretty much just states, you're always going to lose some heat energy to the surroundings. You can't have a 100% efficient engine, namely because your cold reservoir is never going to be zero, and you're always going to lose some. Like you're not going to get 100% of it transferred from the hot reservoir to the cold reservoir. Even thinking about an internal combustion engine, some of the heat energy transferred into an engine cylinder gets just completely pumped out of the engine as exhaust. Exhaust, your muffler, your tailpipes, that's really, really hot after the engine's been running because that exhaust carries so much heat out of the engine with it. All right, let's do one more question. All right, so in this case, a heat engine is operating at its maximum efficiency of 28.8%. All right, this should kind of key us in already. It's talking about maximum efficiency, so I'm probably going to be using this equation or this equation at some point. The cold reservoir of the engine is at a temperature of 295 K. What's the temperature of the engine's hot reservoir? All right, so they're not asking about maximum work. They're not asking for this at all, and they're not even giving us the heat transferred from the hot reservoir. That means the only equation I'm going to use for this is the maximum efficiency one. So 1 minus the temperature of the cold reservoir over the temperature of the hot one. In this case, they want to know the temperature of the hot reservoir. All right, so I need to find TH. I need to get TH by itself. And I'm going to do a little bit of algebra just to get this figured out quick. First thing I'm going to do, I'm going to add TC over TH to both sides. And then I'm going to subtract efficiency from both sides. So I'm going to have TC over TH is equal to 1 minus efficiency. Okay. Now let's multiply both sides by TH. So I've got the temperature of the cold reservoir is equal to 1 minus efficiency times the temperature of the hot reservoir. So I'm almost there. Divide both sides by 1 minus efficiency. Tc over 1 minus efficiency. That's an E. All right, equals the temperature of the hot reservoir. All right, had to do some algebra there just to get the variable I'm looking for by itself. But now I just need to plug some stuff in. Temperature of the cold reservoir, we said it was 295 Kelvin. That's over, parentheses, 1 minus, so 28.8%. If I need that in a decimal, that's 0.288. Okay. Pretty much everything's set up. TH is by itself. I just need to plug this in. So we've got 295 Kelvin, which is room temperature, divided by parentheses 1 minus 0.288, close parentheses, equals 414 point, let's go with 414. 414, and that's in Kelvin. Roughly 100 and some odd Kelvin, or 100 some odd degrees Celsius hotter. That one I think involves some of the most algebra we've done for quite a while, pretty much since the kinematic equations, I'd say, just because it wasn't just as easy as cross multiplying. But yeah, so that's kind of working with work done by engines if we know the differences in the heat transferred from the hot reservoir and the temperature, the heat energy transferred to the cold reservoir. From that, we can calculate efficiency, or if we want to go with maximum efficiency, is if we know the temperature of the cold reservoir and the hot reservoir, we can figure it out that way. So those are kind of the 4 new equations we're going to be working with here. I think we just have one more equation with thermodynamics, and that involves measuring entropy. So good luck.